Hello everyone, this is Group I-27 and I am proud to present our Capstone design project. Our project focuses on developing a low-cost, off-grid solar energy system designed to provide reliable electricity for rural communities in Cienfuegos, Cuba. We aim to provide stable electricity during frequent and prolonged blackouts using a system that is affordable, anti-theft, and easy to maintain.
Cuba is currently suffering from a severe energy crisis where the power supply is significantly lower than the demand, leading to multiple nationwide blackouts through the years. In the community that we'll be targeting in Cienfuegos, these communities experience blackouts from up to 18 to 24 hours and could stretch for multiple days at a time, affecting their daily living because they don't have access to things like refrigeration of their food, lights in the nighttime, and basic communication. In recent times, because of the oil crisis as well, it has become significantly difficult for use of other means of power such as generators, and now with the low income of these communities, they have no other option but to turn to solar power.
Our design focuses on supplying essential energy to 6 households sharing a single building. The system must operate completely off-grid, providing power during long blackout periods remain affordable using recycled or locally available materials. We also had to consider environmental challenges such as high humidity, tropical storms, and corrosion, as well as practical issues like theft and limited access to skilled technicians. These constraints shaped every major design decision, forcing us to prioritize simplicity, durability, and scalability over complexity.
During the design phase, we explored multiple system configurations before selecting the final solution. Initially, we considered rooftop systems, but due to weak structural integrity of the buildings, this was not feasible. We then evaluated different mounting approaches, including a timber frame structure and adjustable mounting systems with slotted designs to allow flexibility in panel installation. The timber frame design was ultimately selected because it is low cost, easy to construct, using basic tools, and does not place additional load on the existing building structure. This process ensured that the final design was not only technically sound, but also practical for real-world implementation.
The final system is a shared off-grid photovoltaic system that's designed to power 6 households. It consists of solar panels, a hybrid inverter with MPPT, a battery storage, a battery management system, along with some protective components such as DC isolators and relays. Energy is then generated by the solar panels, converted and managed by the inverter, then stored in the battery, which is then distributed as AC power, which in turn powers essential appliances such as fans, lights, microwaves, washing machines, etc. The system is then designed to supply approximately 15 kilowatt hours of energy per day, which is enough to support essential loads such as refrigeration and daily needs.
At the core of our system, the electrical design uses a 48-volt DC system with lithium iron phosphate batteries. This voltage was selected because it is low enough to be handled safely by local technicians without specialist training, while high enough to transmit energy efficiently across the system. The battery bank provides 20 kilowatt hours of total storage, with 16 kilowatt hours usable at an 80% depth of discharge limit. This threshold is intentional. Deeper discharge accelerates battery degradation, and given how difficult replacement components are to source in Cuba, extending service life was a core priority. The 16 kilowatt hours of usable capacity covers the system's daily demand of 15 kilowatt hours, sustaining all 6 households through a full 24-hour blackout. Energy flow is managed by a 5 kilowatt hybrid inverter, which handles DC to AC conversion, regulates battery charging and discharging, and delivers stable power to all households simultaneously. The output is 230 volts AC at 50 Hz, compliant with Cuban electrical standards. The inverter integrates maximum power point tracking, or an MPPT, which continuously adjusts the panel's operating point in real time to maximize energy extraction. This is particularly important in Cienfuegos, where temperatures of 30 to 32 degrees Celsius reduce panel efficiency, and where the use of refurbished panels introduces additional performance variability. Safety is addressed through DC isolators on both the solar input and the battery sides, allowing independent de-energization of each section. Overcurrent protection and appropriate conductor sizing are incorporated throughout the system, ensuring the system can be safely maintained over its full service life.
Our first iteration was a roof-mounted articulating design. We moved on from this iteration due to a lack of a full structural understanding of our building, because we were unable to secure accurate blueprints to the home and due to the building's 3-decade-plus age. Our second iteration was a canopy design, such that we had pillars on both sides of the building, tapering into a roof-like structure above the existing roof. We moved on from this design because it was particularly intensive construction-wise and would be difficult to build with locally available materials. Our third iteration was a single mount out on a single side of the home that included all 12 panels. This design was effective but was large and bulky and provided obstruction due to the tapering distance at the bottom. The last iteration we had, and our final iteration, was the single timber frame mount, such that we would have a canopy design on both sides of the home, including 6 panels each, that would provide adequate area at the bottom for entrance and exits into the home.
To evaluate system performance, we analyzed solar energy production using environmental data and panel specifications. Based on calculations shown in the report, each panel generates roughly around 775 kilowatts per year, and a system of 10 panels produces 7,750 kilowatts annually. This translates to roughly 21 kilowatts per hour per day. This exceeds the required 15 kilowatt per hour daily demand that was requested of us. This margin ensures reliable performance even under less ideal conditions such as cloudy weather or system losses. The battery system provides up to 24 hours of autonomy, allowing continuous operation during extended outages. Overall, the system meets all the key performance targets that were set for us, including energy supply, reliability, and efficiency. Final design reflects a balance between performance and real-world constraints. A shared microgrid approach reduces cost and improves efficiency in compared to individual systems. Ground mounting avoids structural risks and improves accessibility. We chose lithium iron phosphate batteries for their long lifespan, safety, and low maintenance requirements. Recycled solar panels help minimize the cost while still meeting energy demands. Each decision was made to ensure that the system is practical, scalable, and sustainable.
Presents a feasible and effective solution to the energy challenges faced by rural communities in Cuba. The system provides reliable power for essential needs, operates independently off the grid, and remains affordable within strict economic constraints. It also demonstrates with strong performance, durability, and adaptability to environmental conditions. While it does not fully replace grid electricity, it significantly improves quality of life during prolonged outages. Overall, this design highlights how engineering solutions can be tailored to real-world constraints to create meaningful impact.